In this video, we're going to look at variable types in Java. We've already looked at Brandon's binary calculator, and we know that we can convert a series of zeros and ones into a decimal-based number. So the example here is that I have the number 159. If I want to take that down to 150, I'll simply turn off the 8 and turn off the 1, and now we have the number 150. If we take a look at everything that has a 1 under it, so 128, 16, 4, and 2, that adds up to 150. So that gives us a number 150, but now what do we do with the number? That's what variable type is all about. So if it's a whole number, a byte, short, int, or a long, it's pretty easy. We have the number that we need. Although 150 would not fit into a byte because 150 is larger than the carrying capacity of a byte. So we'll take a look at what that means in just a moment. Now, what if we need to hold a decimal value, something after the decimal point? If that's the case, we need to convert these zeros and ones to something that makes sense in that domain of decimal point values, and in that case, the type we're going to need is a float or a double. If we wanted to represent a letter, something that we'd see on our keyboard, then we'll need the variable type char, C-H-A-R. And then there's a simple way to indicate just true or false, and that is a boolean. So these are the 8 primitive variable types that we have in Java. Let's look at them in more detail. First of all, we know that a variable type is something that is used to declare a variable. So declare a variable means we are allocating space in the computer's memory, and we're giving that space in memory a name. In this case, we have age. And we're giving it a type, and that's the subject of this video, the type, which is how we convert that number 150 into something that's usable. In this case, we see the type is int. Okay, so let's explore each of these data types. Where I am on my UC homepage, so ucjava.com, and from there I'm going to go to 32IT205, which incidentally was one of the first computer programming 1 courses I taught. No longer offered under that name, but nonetheless. Topic 3 is data types, or we can simply go up to the very top here. Variables and type, data type intros, and then we're going to go to whole numbers. So whole number, I have these in, I realize this is kind of a funny order, but I have these in a certain order. Each of these represents a whole number, or in other words, something that does not have a decimal value. So the smallest one is a byte, which literally is 1 byte in the computer's memory. 1 byte is 8 bits. Okay, what's a bit? Well, essentially, this is a byte right here. So a byte is made of 8 bits. A bit is something that can be either a 0 or 1. So count with me. 1, 2, 3, 4, 5, 6, 7, 8. Sure enough, this is a 1 byte data type. Okay, if I were to fill in each of these with a 1, we'd see our number over to the right becomes 255. So 255 is the largest amount of data we can store in a 1 byte data type that is unsigned. But in Java, we don't have unsigned types. What does unsigned mean versus signed? Signed or unsigned means we reserve this leftmost bit for a positive or negative indicator. Because that is reserved in Java, let's go ahead and mark that as a 0, and we see now the highest positive number we can store in a byte is 127 because we're reserving that leftmost bit for sign. Let's see how that corresponds on my diagram here. Sure enough, for a byte, the number range is negative 128 to positive 127. Now one thought, why is the negative value 1 greater than the positive value in each case? Kind of a funny thing. There are actually 128 positive numbers, but we have to take a little bit of liberty there because one of those positive numbers is not really positive. It's simply the value of putting 0 in every single bit, which means we end up with 0 is the number that's represented by all bits being 0. So if we include that, there's actually 128 on the negative side, 127 on the positive side, plus the number 0. That gives us 256 unique numbers that we can identify with a byte. Okay, now a short is 2 bytes. So a short takes us to quite a dramatically longer range of data, minus 32,768 to positive 32,767. Now you might say, wait a minute, it's only one more byte than a byte data type. Shouldn't it just be double 128? Why is it such a dramatic increase in size to 32,768 on the negative side, 32,767 on the positive? Well, the reason is, I go back to my decimal converter and I added a new kind of column down here at the bottom, where I simply added 2 more bits. Not all 16 bits that a short would have, just 2 more bits. Let's see what happens when I fill every bit with a 1, and look at the number that we come up with. 1023, which is significantly more than if I simply have a byte data type and I fill each of those numbers with a 1. You see 255. Of course, we know we reserve that 1 for sign, and even if we do the same thing here, we still end up with a dramatically different number. So, while a short is only 1 byte greater than a byte, in other words, twice the size of a byte, we have to consider those extra bits are allocated towards much bigger numbers, which is what gives us this greater capacity of 32,767. Now, here's a consideration. What if I tried to store 33,000 in a short? What would happen? It essentially ends up flipping the odometer. It kind of goes around to negative at that point, which is not a desirable outcome. As a matter of fact, one time I remember this very specifically was a snowstorm in Cincinnati, December 21 to 24th, 2004. If you think about that date, it's right before Christmas. And I remember very well at the time I lived in Erlanger, and it just kept snowing, snow and ice, where it was about 12 inches of snow, a quarter inch of ice, and then 12 more inches of snow. It snowed so much the interstates were not even clear by the time Christmas came around. Even the major roads were not clear. With a major airport in Covington, Kentucky, the airport essentially shut down for a day because of the snow. But what was interesting was this ComAir computer system crash. ComAir, which is no longer in business now, but at the time, ComAir was a Delta subsidiary that was mostly regional flights, generally out of New York, Cincinnati, and Orlando, kind of the eastern part of the country. And so smaller, kind of 76-seat jets and lower, a lot of 48-seater jets. But once the snowstorm was gone, ComAir was still shut down for several days. And the reason was their rescheduling system for aircraft and for personnel could only hold 32,767 changes. And because of the snowstorm, because they had canceled so many flights, they had to reschedule more than 32,767 aircraft crew, aircraft, and everything else that has to be rescheduled. Now, that number didn't mean a lot to most people, but I remember reading an article that said that their reservation rescheduling system had this upper limit of 32,767. And immediately I thought, okay, they had 2 bytes allocated for their rescheduling system when they should have maybe had 4 or 8. So it was simply a case where an entire airline was ground to a halt for several days after the snowstorm, simply because the programmer at the time had chosen to use a short instead of an int or a long to store the data. Now, teaching this course in Cincinnati, it's inevitable that I would eventually have a ComAir employee in my class, which I did. And this employee told me that they were well aware of the issue and that they had tried to upgrade to a newer rescheduling system because the one that they were using was one that they used when it was a much smaller airline. And he said that rescheduling system had been, or the update of that rescheduling system had been delayed by about a year, and that's when this failure happened. It happened during this time where that upgrade had been delayed. So, little backstory there. Of course, a lot of finger pointing you could imagine going on, but nonetheless. Okay, an integer. Integer is probably the most common type because it strikes a good balance between range and also the resource that it's consuming on the computer. An integer is essentially plus or minus 2.1 billion. So this is the most common that we use because most of the things that we need to do, like compute a salary, compute maybe a distance, anything like that, most of these things will be in an int data type, which is 4 bytes. Now, one above that is a long data type, which is 8 bytes, and you see that can hold some humongous number. I don't even know what to call that number, but it's a very large number. Now, what if you need to store something greater than that number? You can use something called a big integer, which is not a primitive type. Primitive means you can essentially trace it back to zeros and ones pretty easily. A big integer is a bit more complex than that, but it can hold an infinitely large number. Okay, that's question number 1. Question number 2, if we know the com-error story here on short, why don't we just use a long all the time? Why don't we just use the greatest data type that we can use? Well, of course, everything's a trade-off. It would be great to use longs all the time, but then we're constantly using 8 bytes. When you think of something that's a multi-user piece of software, maybe a server-side or a cloud-side component that's supporting mobile devices, and maybe every time you have a mobile device connect, you need another one of these variables, think about how quickly that can multiply out. So we want to be good stewards of the resources that we have. We want to use just enough, but not too much. And that's why we have so many decisions here. In my personal experience, int, use it all the time, probably 95% of the time that's what I use. Long, I've occasionally needed this when I'm computing check digits. So some large computation where we simply want to make sure that everything adds up, occasionally I've used a long for that. Short, not too much, but I will say I have used it in mobile programming, just because in mobile programming we do have to keep an extra eye on resources, because mobile phones are small, they don't tend to have the memory that a traditional laptop would have. Byte, I can comfortably say I've never had a good use for byte, me myself. Now other people may, but I've just not had a good use for byte. So those are the whole number types. Let's take a look at the floating point types. The floating point types are float and double. This is kind of an interesting one because the range is a little bit tricky because we have to keep in mind that we have both a whole number component and a decimal component. One thing I'll warn you about is floating point arithmetic can be a little bit painful. I can summarize floating point arithmetic by saying, how do you store 1 divided by 3 if you have a finite place of memory in which to store that? In other words, 1 divided by 3 is 0.3 continuous. So 0.3333333 into infinity. The trick is, what if you don't have to infinity? What if you only have maybe 4 positions? Then you have 0.3333 over 10 thousandths, which is 3,333 10 thousandths, if that makes sense, which is not exactly 1/3. It's close, but not exactly. And that's an issue that we have with floating point types, is there is a little bit of inaccuracy in there. So we don't want to use floating point types anytime we're talking about money. If we're talking about money, we prefer something else like big decimal. Okay, but nonetheless, if you're doing a quick computation like a Celsius to Fahrenheit conversion, something like that, floating point type will be fine. So we have a float, which is 4 bytes, and a double, which is 8 bytes. When I use these, I typically use double, but there again, if I'm doing a financial computation, my preference is to use big decimal. Okay, just a couple more to go. So we have char and boolean. Char is a single character. So it could be an A, B, C, D, something like that. So for this, we can go to the binary calculator, and let's go to our sheet number 3 here. And there are a couple of different encoding mechanisms that we have. So we have ASCII, the American Standard Code for Information Interchange, which was the... now, by ASCII, what do I mean? What I mean is, or by character encoding, what do I mean? What I mean is we take a number, maybe a number that we got from our binary to decimal calculation here, and we have some map that goes from number to letter, maybe even number to lowercase letter. So number to uppercase letter, number to lowercase letter. For ASCII, it decided to do this numbering one way, and I don't recall the exact details, but essentially it put the uppercases first and then the lowercases. At that time, when this character encoding came out, IBM was kind of the big elephant in the room. IBM was the company that was very dominant, kind of like you see every 10 years there tends to be a different dominant company. Microsoft was dominant, IBM was dominant, Apple, Amazon. You hear a lot of different companies that are dominant. You think they'll be dominant forever, but 10 years later you find somebody else is. Nonetheless, IBM came up with their own encoding, which was their mapping of letters to numbers. And their encoding was kind of annoying because they just switched the uppercase and the lowercase around just to make it harder to leave the IBM platform. These days we have Unicode. So Unicode is essentially a 2-byte fixed or variable way to map numbers to letters. Now when I say numbers to letters, we kind of have to exercise some liberties on letters. And remember that we're talking to an international audience. So it could be the letters that we're used to in the United States, or it could be the enya with the tilde that's used in most Spanish-speaking countries, or it could even be Arabic numbers, Chinese, simplified, or Mandarin, anything like that. It can handle any of those characters. Why? Because we know with 2 bytes, we have negative 32,768 to positive 32,767 is our range of addressable numbers, or in other words, a total of 65,535 addressable numbers, which means that's the number of characters that we can map in Unicode. So ASCII, EBCDIC, or Unicode, right now a Unicode flavor that's very popular is called UTF-8. That's simply a way that we can say, okay, when I do my binary math, that binary math is going to come to a number. Now I take my encoding, which is a map from number to letter. Still a number under the covers, but to us as humans, what we see is a letter. There are a couple special characters like backspace, tab, line feed, carriage return. There are a few special characters. We'll take a look at those deeper when we look at strings. Now, one thing I will say, character, we want to enclose the value in single quotes, where it's just going to be a single character for a car data type. If we want to store an entire word, we need to use something called a string. So character is just a single character. Boolean's a quick one. Boolean just means true or false. That's it. It's just kind of a binary yes or no, a true or false. So those are the 8 primitive types, and we know we also have this type called string. If I take a look at my program that we looked at in a previous video, you see zip code. Could I make that an int? I sure could. Can I make that a short? Yeah. Short, actually, no, it doesn't like a short, does it? Because what we see here is we see something called possible lossy conversion. That one's a bit confusing to get into at the moment. So let's just go ahead and keep that as an int. Can we make it a long? Yep, we can make it a long. Can I make it a double? I can make it a double. I wouldn't recommend that because it's a whole number type, so double kind of feels like overkill. But you see, I can make that type a double. Can I make it a float? I can make it a float. Can I make it a Boolean? I can't make it a Boolean because a Boolean needs to be either true or false. We'll go ahead and turn it back to an int here, and then down below what I'm going to do is say car, and then I'll say my character equals, and we'll say C. So you see here I've declared a variable of type car. Notice I can only put one letter in there. As soon as I say character, as soon as I put multiple letters in there, even though I misspelled it, it won't let me do it. So a character is only for one character, or one letter, and single quotes. We can put a number in there. We can put a symbol if we want. We just have to remember to have it in single quotes. A string is multiple characters. We didn't see this on our previous slides, but I could say string first name. Notice doing that in lowercase. Now for a string, we use double quotes, and a string can contain multiple letters. So string first name equals Brandon, like you see here. So those are the variable types. The ones we're going to use the most in this class are string, int, and double. The others we won't use as much, but string, int, and double are the ones that you're going to see most frequently. Just a few things to wrap up with then. Sometimes we have easy conversion. If we're storing an int variable into a long, no problem. An int is 4 bytes, a long is 8, so no problem. What if we want to store a long into an int? A long is 8 bytes, an int is 4 bytes. There's a chance that we could lose some data. We could lose data if the value that we're storing is greater than the capacity of an integer. So just a moment here. So in other words, if I have a long, and this long variable contains 3 billion, and I try to store it in an int, where an int can only contain up to 2.1 billion, it's going to say possible lossy conversion, and it's going to require a cast. Those are kind of ugly topics I don't want to talk about just yet. Just want to bring it up early so we can touch on it a little bit later. Also, we remember we do not want to use floating type for monetary calculations. Use big decimal. As a matter of fact, I shy away from floating point for other things where we have a decimal value, like GPS. Because GPS, oftentimes the value after the decimal is important. So try not to use floating point for that. Big decimal is a better choice. So that's a quick look at types. Hope you found this helpful. In the next video, we'll take a look at some mathematical operations. I look forward to seeing you then. Thank you.